Okay guys, welcome to your video lesson on section 811 and then 8.3 part 1. This is going to be a review of imaginary numbers and then also an introduction into what we call polar form of a number. So let's start with a couple of facts about complex, or sometimes just referred to as imaginary numbers. Just to give you an example here, in number 1, in a complex number 3 plus 2i, the number 3 is called the real part. The number 2 is called the imaginary part. And the way that you can kind of distinguish between those is the fact that the 3 does not have I and the 2 does have I. And that number I is called the imaginary unit. And we have a very nice definition for this imaginary unit as we look at number 2 now. The definition for I is that it is equal to the square root of -1. And so that leads to several other really nice facts. For example, if you were to square both sides of that definition, of that equation, you would get that I squared is equal to -1. If you were to multiply both sides of that equation by I, then the left-hand side would be I squared times I, which would give you I cubed. And then -1 times I would give you -I. So I cubed, by definition, is equal to -I. And then, if you were to take that equation and multiply both sides by I, then what you would end up with is I to the third times I is equal to -I times I. Okay, well, I cubed times I is going to give you I to the fourth, and then -I times I is going to give you -I squared, and we know that back over here, I squared is equal to -1. So the opposite of -1 will equal to 1. And it turns out that these rules repeat themselves. And so what I mean by that is that if you were to keep going here, you would see that I to the fifth was just equal to I. I to the sixth then was equal to -1. I to the seventh would be -I, and I to the eighth would equal to +1. And so what you're going to end up seeing is that I raised to any power of 4, so just, to give you an example, let's just say 12, that's always going to equal to 1. Any multiple of 4, I think a second ago I said power. What I meant to say was a multiple of 4. If that's the exponent on the imaginary unit, then the result is going to be 1. Just like if you had, let's just say, I to the 20th. Since 20 is a multiple of 4, then I to the 20th is going to equal to 1. So that fact is going to be very important later on when we work some problems. So keep that in mind. So number 3, all real numbers are complex numbers. If it does not have an imaginary part, that's what we call a real number. If it does have an imaginary part, then it would be under the umbrella of what are called complex numbers. And then finally, fourthly, the product, meaning when you multiply a complex number and its conjugate, the result is always a non-negative, meaning either positive or 0, real number, meaning no imaginary part. Okay, so let's see why that's the case. If I take any number, complex number, a plus bi, and I multiply it by its conjugate, which in this case would be a minus bi, let's see what the result is. So if I take a times a, then that's going to give me a squared. A times -bi is going to be -abi. Bi times a is the same thing, just positive, and so you can see those two terms are going to cancel out. And then bi times -bi is going to be -b squared times I squared. Okay, well, as we mentioned before, -abi and +abi are going to cancel, and so this is going to equal to a squared minus b squared times I squared, which by definition is equal to -1. And so simplifying that further gives us a squared plus b squared, which, as you'll see, has no imaginary part, so it is a real number. And because it's the sum of two squares, that means it has to be non-negative. And so this will be the case for any imaginary number that you multiply by its conjugate. The result will always be a non-negative real number. Okay, so in example 1, we're going to jump into just some review of imaginary numbers. So, some of these problems are going to be pretty basic as we work through these, but just as a reminder on how to do some of these things as we focus in on imaginary and complex numbers today. In example A, we're just adding two imaginary numbers. And so when we add imaginary numbers, we're just adding their corresponding parts. And so in this first imaginary number, 4 is the real part. And in the second imaginary number, 9 is the real part. And so when I add those, I get a real part of 13. For the imaginary part, in the first, trying to get a different color here. There we go. In the first imaginary number, we've got a -4 for an imaginary part. And in the second number, we've got a plus 6i. And so that's going to give us a positive 2i for our imaginary part there in letter A for the answer. Okay, letter B, we're going to do the exact same thing, except this time we are subtracting, so you just got to be real careful not to make any sign errors. 9 minus 2 will be our real part, so that will give me 7. And -2i minus 2i will be my imaginary part, and that will be minus 4i. Okay, in letter C, we're going to be multiplying, so we've got 7i times 9 minus I, and so we're just going to distribute here like we normally would. 7i times 9 is going to give me 63i, and 7i times -i is going to be minus 7i squared. But by definition, what I know is that I squared is equal to -1. And so this is going to become 63i plus 7. But the directions, if you'll look back up here, say to write it in this format, a plus bi, which means that the real part has to come before the imaginary part. And you've got to be real careful not to make that mistake on your online homework and make sure that you type it in the correct format, which would be the real part coming before the imaginary part. Okay, on letter D, we've got two binomials, which means we're going to have to FOIL this out. And so starting with the first terms, 8 times 1 gives me 8. 8 times I gives me 8i. -2i times 1 is minus 2i. And so I see now I've got some like terms to collect. And then -2i times I is going to be minus 2i squared. Okay, so a couple things. I know, first of all, that I squared is equal to -1, as we just mentioned here a minute ago. And so that term is going to become a positive 2. And then I've got my 8 down here. And in the middle, I've got two terms that are i's. And so if you look here, we can combine those like terms to get a positive 6i. And then adding these imaginary parts, this 8 and this positive 2, we're going to get our final answer of 10 plus 6i. Okay, E and F are going to be division problems, and so when we divide imaginary numbers, what we end up doing is making it into a multiplication problem by multiplying by the conjugate of the denominator. And so if I multiply by the conjugate of 1 minus 3i, that would be 1 plus 3i. And in the numerator, I'm just going to distribute. So 2 times 1 gives me 2, and 2 times 3i is going to give me 6i. In the denominator, I'm multiplying conjugates. So I know the answer is going to be a non-negative real number given by a squared plus b squared. And so a squared is going to be 1 squared plus b squared is going to be 3 squared, and that is going to give me 10. Now, to write this in a plus bi form, we're going to split this through the numerator like we normally would. And so this is going to be 2 divided by 10 plus 6i divided by 10. And reducing those fractions is going to give us 1/5 plus 3/5 multiplied by I. And some of you are going to have the question, do I need to put the I in the numerator along with the 3 and write it so that it looks like this? That would be the exact same thing as what I wrote and boxed. So whether you want to write it like this or like this, Either way is perfectly fine, and both of them will be accepted for full credit. Okay, letter F, we've got 52 plus I divided by I. So again, we're going to take the same approach here of multiplying by the conjugate, which would be negative I. And in the numerator, we'll distribute. So 52 times negative I will be negative 52I. And then positive I times negative I will be negative I squared, divided by I times negative I, which is also negative I squared. And so we know that I squared is negative 1. So this is going to be negative 52I minus negative 1 divided by the opposite of negative 1. And so a lot of nice things are going to end up happening here. First of all, this minus and that minus become plus, and so that's going to give me a real part of 1 minus 52I. And in the denominator, the same thing is going to happen. Minus and minus become plus, and so dividing by 1 really doesn't do anything. We end up with our answer of 1 minus 52I. Okay, on letter G, we've got 10 plus I squared. And so remember that anytime we're squaring something, that just means we're going to multiply it by itself. And so we'll have 10 plus I times 10 plus I. Notice that these are not conjugates, and so I'm not going to be able to just do a squared plus b squared. I'm going to have to actually FOIL this out. So 10 times 10 will give me 100. 10 times I will give me 10I. I times 10 will also give me 10I. And I times I will give me positive I squared, which I know is going to become a negative 1. So this is going to be 100 plus 20I, subtract 1, since I squared is negative 1, and so that means I'm going to have 99 plus 20I. Okay, letter H, we're going to use that fact that we discovered earlier, that I to any any multiple of 4 is going to equal to 1. So I to the power of any multiple of 4 is going to equal to 1. So really we could say I to the 4k, where k is, k is an integer. We could say that that's a true fact. And so here's what we're going to do. We're going to take this exponent, this 25 on this letter H here, and we're going to figure out how many times 4 can go into 25 evenly. And so this is going to really become I to the 4th, and 4 goes into 25 evenly 6 times, and that's going to get me up to 24. So this right here is going to give me I to the 24th, which means that there is one I left over to get us back up to 25. Okay, what I'm going to do next is basically use the fact that this I to the 4th is equal to 1, and so this is going to be 1 to the 6th power multiplied by I, and 1 to the 6th, of course, would just be 1, and 1 times I is going to equal to I. Okay, so I to the 25th, then, must also equal to just I. Okay, now, no pun intended here, but problem letter I is equal to, and what we want to do is we want to simplify I to the 6th minus 3. So once again, we want to figure out how many times does 4 go into 6, and that would be once. And that means that there are going to be 2 of those left over. And so this is going to be 1 to the 1st power times I squared, which is negative 1. And that's going to give me negative 1. And so I to the 6th is negative 1. And then subtract the 3 is going to equal to negative 4. Okay, in example 2, we're going to simplify some radicals that involve negative numbers. And so really, this is not going to be any different than what we've done in the past in simplifying radicals. It's just that because it's the square root of a negative number, we're going to have to include an I in our answer. So letter A is very straightforward, square root of negative 16. 16 is a perfect square. I know that the square root of 16 is 4. And then the fact that we've got the negative underneath means that I need to have an I there on my answer. So maybe just to give you a little bit of a better idea of what's going on, this is 16 times negative 1. I'm pretty sure you would agree. And then square root of 16 is 4, and the square root of negative 1, by definition, is equal to I. Okay, on letter B, we're looking, 112 is not a perfect square, so we're going to be looking for the biggest perfect square that goes into 112. And if you do that, what you're going to end up finding is that it is 16. And 16, I believe, multiplied by 7 is equal to 112. You can just double check that for yourself. And so what this becomes is 16 times 7 times negative 1. And so now square root of 16 is 4. 7 is not a perfect square, so it's got to stay under the radical. And then square root of negative 1 is our I. So 4 square roots of 7i would be the result there. Okay, letter C, you need to also find the biggest perfect square that will evenly go into 147. What you end up finding out is that it is 49, and so this is going to equal to 49 multiplied by 3 multiplied by negative 1. And so square root of 49 would be 7, so that's going to come out as a regular 7. 3 is not a perfect square, so it's got to stay under the radical, and square root of negative 1 is equal to I. Okay, example 3 and example 4 are going to be pretty straightforward. We've got an imaginary number w, 7 minus 6i, and we want to write the expression w plus w bar in standard form. So this is pronounced w bar because of the bar over the top, and what that means is conjugate. So that notation, whenever you see the bar over the letter, means conjugate. And so in this particular problem, w bar is going to equal the conjugate of w, which will be 7 plus 6i. So when we want to do w plus w bar, that's going to equal to our definition in this problem for w, added to the conjugate of w, which will be 7 plus 6i. And so we're just adding these two imaginary numbers together. And so if we add the imaginary parts first, that would be the 7 and the 7, and that's going to give us 14. And if we take the imaginary parts, negative 6i plus 6i, those are going to cancel, and so this will not have an imaginary part. The answer will just be a real number of 14. Okay, in example 4, we're wanting to take the imaginary number 1 minus 3i and multiply it by z bar, which again would be the conjugate of z, which in this case would be 1 plus 3i. And so whenever we write that we want to multiply z by z bar, this is going to equal to our definition in this problem for z multiplied by the conjugate of z. And since I am multiplying two complex conjugates together, I know the result is going to be a non-negative real number, a squared plus b squared. So if I take 1 times 1, that's going to be 1, and then negative 3i times 3i is going to end up giving me plus 9, and so this is just going to equal to 10. Okay, example 5 will get us into the beginning part of section 8.3. And so what we're going to do here is we're going to take this complex number, we're going to plot the number in the complex plane, which I'm going to explain here in just a minute, and then we're going to write in polar form. And so that's going to take us back to section 8.1 and our conversions into polar, namely that r is equal to the square root of x squared plus y squared, or perhaps using better notation in this case, the square root of a squared plus b squared. Sorry about that. And also that the angle theta is equal to the tan inverse of b divided by a, or y divided by x, if you want to think about it like that, or imaginary part divided by real part. However you want to think about it is going to be what we have there. And so what is polar form? Polar form is r multiplied by cosine of theta plus I times the sine of theta. That's what polar form looks like, and that's what we're going to be writing these four imaginary complex numbers in this problem. So in letter A, we've got 4 plus 4i, and so what that looks like is the ordered pair in the complex plane 4, 4, where this is the real part, and this is the imaginary part. And so when I go to plot this, this is the real axis, and this is the imaginary axis. Kind of like when you do the xy plane, the x is horizontal and the y is vertical. In the complex plane, the real axis is the horizontal axis, and the imaginary axis is the vertical. So if we were to come over 4 on the real axis and then go up 4 on the imaginary axis, then that would be our complex point for 4. Okay, so how do we get that into polar form? Well, the first thing we've got to do is we've got to figure out what the radius is. And so the radius is going to equal to the square root of a squared plus b squared, which is going to equal to the square root of 16 plus 16, which is 32. And we want to go ahead and simplify that, which means we need to find the biggest perfect square that will go into 32, which would be 16 times 2 is what's going to get us to 32. And so that's going to equal to 4 square roots of 2. Okay, the theta is going to equal to the inverse tangent of the imaginary part, which is 4, divided by the real part, which is also 4. And so this is going to be tan inverse of 1, which is going to equal to pi over 4, since the tangent of pi over 4 is equal to 1. And so this number in polar form is going to be written as follows. 4 square roots of 2 multiplied by the cosine of that angle theta, pi over 4, plus I times the sine of pi over 4. Okay, in letter B, this one's going to be a little bit actually easier to do. So negative 2i, what would you say is the real part to that number? Well, hopefully you said 0, because there is no real part. There's only an imaginary part, 0, negative 2. And so when we go to plot this, we're going to go on the imaginary axis down 2 and plot our point right there. And so this is actually pretty straightforward, because just by looking at this plot, we're going to be able to figure out what the radius is, and hopefully you can look at that and say that the radius is 2. And we're also going to be able to tell pretty easily what the angle is, and since it's down here on the negative y-axis, that tells me that the angle is going to be 3 pi over 2. So in polar form, this is going to look like the following. 2 multiplied by cosine of 3 pi over 2 plus I times the sine of 3 pi over 2. Okay, letters C and D are going to be questions that you're going to need to do with your calculator because we're not going to be able to find the angle without using a calculator. And so in this first problem, we've got 2 minus 5i, which in the imaginary or in the complex plane is going to be the point 2, negative 5. And so like we normally would, we'll come over 2 on our real axis and then go down 5 on our imaginary axis and plot our point there, 2 and negative 5. And the next thing that we want to do is we want to figure out what the radius and the angle are so that we can write it in polar form. And so r is going to equal to the square root of a squared plus b squared. And doing some simplifying, that's going to give me the square root of 4 plus 25, which is 29. And then the angle, which I'm not going to be able to do without a calculator, is going to be tan inverse of that imaginary part divided by the real part. And so make sure in your calculator that you are in radian mode, because if you're not, then things are going to go pretty bad for you. And so, unfortunately, I've got sort of a calculator here that I don't really understand how to switch back and forth between radians and degrees, and I have no way to pause this video. So to tell you the truth, I'm not going to be able to calculate this for you, so what I'm going to just do is call this theta and write my answer as follows. So square root of 29 multiplied by cosine of that angle theta, which you get from the calculator, and then plus I times the sine of that angle theta, where the theta that I'm talking about is whatever you would get when you typed this into the calculator, making sure you are in radian mode. Okay, letter D is very similar, so I'm going to skip that example, but I'll just tell you that your plot in the imaginary plane is going to be in quadrant 2, so -3 here, and then 1, 2, 3, 4, 5, 6, 7, 8 will be up here. And then your radius will equal to the square root of -3 squared plus 8 squared, which is going to be the square root of 73. And then your angle, again, you'll need a calculator in order to do this. You're going to get tan inverse of 8 divided by -3. And so that is going to give you your answer once you write it in polar form as follows. Square root of 73 multiplied by cosine of whatever that angle happens to be when you calculate it, plus I times the sine of theta. Okay, in example 6, we're going to be going the other direction, taking a number that's in polar form and writing it in rectangular form, which is just a plus bi. Okay, so on letter A, we've got 6 times cosine of 7 pi over 4 plus I sine of 7 pi over 4. And so what we're going to do, first of all, start off by doing is actually evaluating what cosine of 7 pi over 4 and sine of 7 pi over 4 are. And so for 7 pi over 4, I know that's in quadrant 4. Cosine in quadrant 4 is positive, and the reference angle is pi over 4, so that's going to be positive square root of 2 over 2. And then sine of 7 pi over 4, same story. It's in quadrant 4, but that means it's going to be negative. So I'm going to actually back up here, and I'm going to erase my plus sign, and I'm going to put a minus sign, and that's going to be square root of 2 over 2, and then don't forget the I. And then if I distribute this 6, I'm going to be done. So 6 over 2 is going to give me 3 square roots of 2 minus 3 square roots of 2 multiplied by I. Okay, number 3, we're going to do the same thing. So 3 cosine of pi over 2 plus I sine of pi over 2. And so this is going to be 3 times the cosine of pi over 2, which is 0, plus I times the sine of pi over 2, which is 1. And so if you need a quick refresher of why that is, because I know it's been a second since we've done the unit circle, pi over 2 is up here at the top of the unit circle, and that's the point 0, 1, and cosine is the x-coordinate, and sine is the y-coordinate. So this is going to end up equaling to no real part, and then an imaginary part of 3i. Okay, letter C, you're going to also need a calculator. This time it's going to need to be in degree mode. And to tell you the truth, going back and looking at C and D, you might actually need to be in degree mode. You just need to kind of look and see the directions on your online homework, but I actually kind of want to say that you might actually need to be in degree mode. And so please just double check that as you're working your homework. When you do this calculation and you hit the second tangent button, I actually am thinking now that you need to be in degrees. And so just double check that for me and make sure you're paying attention. And so literally all you're going to do here is just distribute this 0.2 here. And so you're going to have 0.2 multiplied by cosine of 160 degrees plus 0.2 times the sine of 160 degrees. And don't forget to put your I on the end of that imaginary part. Okay, that's going to do it for section A11 and the first part of 8.3. Please let me know if you have any questions. Bye, guys.